Let's look at some additional examples of induction. So our example 2 is going to be the following. We want to demonstrate that 3n minus 3 to the power n minus 2n minus 1 is divisible by 4 for all n in n. So it doesn't matter which natural number n is, the expression 3 to the power n minus 2n minus 1 should always be divisible by 4. So we're going to use mathematical induction. And again, what we need is to demonstrate two steps. Step number 1, basis of induction. And let's see what we can see here. So we're going to choose n to be equal to 1. If n is equal to 1, then 3 to the 1 minus 2 times 1 minus 1, that is equal to 0. And of course, 0 is certainly divisible by 4. So that means that the basis of induction holds. So this is okay. Number 2. Now we look at the induction step. And what do we have here? We're going to assume that the statement Pn holds, right? So that means that 3 to the power n minus 2n minus 1 is divisible by 4. So assume that this is true, right? So then there exists a number k, a natural number k, such that 3 to the n minus 2n minus 1, this is equal to 4k, right? Because that's what it means to be divisible by 4. And so we need to demonstrate that the statement Pn plus 1 is true. And that means that 3 to the power n plus 1 minus twice n plus 1 minus 1, that this is divisible by 4. Right, so that is what mathematical induction asks us to do. Okay, so let's see. What do we have? So we start with 3 to the n plus 1 minus 2 n plus 1 minus 1. And I'll have to manipulate this expression and use the fact that the nth step of the statement is true to conclude that the n plus first step of the statement is true. Well, so we can rewrite this in the following way. I'm going to write 3 to the power n plus 1 as 3 times 3 to the power n minus 2n minus 2 minus 1, just opening the parentheses. And then I'm going to use the fact that the statement Pn is true. So Pn is true that means that 3 to the power n can be expressed in terms of k and n. Right, so we have 3. It should be times 3 to the n, but I can solve this for 3 to the n, and if I do that, I'm going to get 4k plus 2n plus 1, right? Because that's what 3 to the n is from my assumption. Still, minus 2n, minus 2 minus 1, so minus 3. Okay, now what is that? This should be, now if I open the parenthesis, 12k plus 6n plus 3, still minus 2n minus 3. 3 cancels out, and 6n minus 2n is 4n. So this should be 12k plus 4n. And I can factor out 4 out of this to get 4 times 3k plus n. Well, but 3k plus n, this is a natural number. And so then 4 times a natural number, this is divisible by 4. So this induction step is also okay. So if both bases of induction step are going to hold, then by mathematical induction, we conclude that our original statement is true. So therefore, 3 to the n minus 2n minus 1 is divisible by 4 for all n in n. So we proved our assertion, and we will indicate the end of the proof by drawing a square box. This is just a covert notation, just to indicate that your proof is complete. Let's do the next example. Example 3. Let's show that the expression, let's say 5 to the n minus 3 to the n, that this is divisible by 2, again for all n in n. Again, we use induction. So let's look at the basis of induction first. And what we see is that the first statement is 5 to the power 1 minus 3 to the power 1, which is 2. So this is divisible by 2. And so the basis of induction then is true. Number 2, induction step. So here we're going to assume that, again, the end in this statement is true. End statement is that 5 to the n minus 3 to the n is divisible by 2. And what does it mean to be divisible by 2? There exists a number k in n such that 5 to the n minus t to the n is equal to 2k. Okay, so now we need to show the n plus first statement. So we need to show so what is the n plus first statement? That's 5 to the power n plus 1 minus 3 to the power n plus 1. That this is divisible by 2. And once again, in showing this, we must use the previous statement. Okay, so from the original assumption, I can actually write that 5 to the n is 3 to the n plus 2k if I solve for 5 to the n. So then 5 to the n plus 1 minus 3 to the n, what is that? That's 5 times 5 to the n, oh, sorry, 3 to the n plus 1, minus 3 to the power n plus 1. But by my assumption at the nth level, now I can rewrite 5 to the n as 3 to the n plus 2k. So this would be 5 times 3 to the power n plus 2k minus 3 to the power n plus 1. Opening the parentheses, this is 5 times 3 to the power n plus 10k minus, and 3 to the power n plus 1, again, I can write as 3 times 3 to the n. So then by looking at the first term and the last term, they have a common factor of 3 to the n. So 3 to the n times 5 minus 3 plus 10k. And then 5 minus 3 is 2, so this would be 2 times 3 to the n plus 10k. And there is a common factor of 2 here, so 2 times 3 to the n plus 5k. Now, 3 to the n plus 5k, this is a number which is certainly a natural number. It's one of the counting numbers. And so if my number 3 to the n plus 1 minus 5 to the n plus 1 minus 3 to the n plus 1 is equal to this, then certainly the outcome is divisible by 2. So divisible by 2. And so therefore the induction step is okay. And so we conclude using mathematical induction that our original statement 5 to the n minus 3 to the n is divisible by 2 for all n in n. All right, and then one final example, example number 4. And let's look at the example in a book. Let's say we want to show that the sine of nx in absolute value is always less or equal than n times absolute value of sine x. So for all n in n. Again, we're using the induction. So I'm just writing induction as a shorthand for mathematical induction. And once again, we have to demonstrate two steps. Basis of induction, in this case, absolute value of sine, we're looking at the first step, absolute value of sine x, n is equal to 1, less or equal than n is 1, so the right-hand side, n times sine x, is also absolute value of sine x. This is certainly true, so that means basis of induction is going to hold. It's okay. Number 2, now we look at the induction step. And I hope that you already appreciate that basis of induction is typically a rather easy thing to do, to show, but an induction step involves some algebra, which sometimes might be a little bit lengthy, but it's just an algebra. Okay, so let's see how that works here. I'm going to assume that I already know that sine of nx is less or equal than n sine x. So the nth statement is true. And what we want to do, we want to use this fact to show that the same relationship holds at the step n plus 1. So sine n plus 1 x is less than n plus 1 times absolute value of sine x. Right, so we need to prove this. Okay, so let's work with absolute value of sine of n plus 1 x. Well, what is this? That is absolute value stays. If I distribute x, then I get sine of nx plus x, absolute value. And you may or may not remember the formula for the sine of the sum of two numbers, so sine of a plus b. What is that? That's sine of the first number, so sine of nx, times cosine of the second number x, plus cosine of the first number, cosine of nx, times sine of the second number, sine x. All right. Okay, so this is what we got. Now, if I add two numbers and I take absolute value of a sum, then you might recall that the absolute value has a property that absolute value of a sum must be less or equal than the sum of the absolute value. So this is less or equal than absolute value of sine nx cosine of x plus absolute value of cosine nx times cosine of x. This is something called a triangle inequality, which we're going to establish in maybe even the next lecture or next couple of lectures. All right, but then also we know that actually this is going to be equality. If I take absolute value of the product of two numbers, then absolute value of the product must be the product of absolute values. So this is the same thing as absolute value of sine nx times absolute value of cosine x plus absolute value of cosine nx times absolute value of cosine x. Made a mistake. Cosine this cosine is sine actually. So sine x and sine x here. All right, so what do we know from this? We know that cosine of something is always less or equal than 1. So this cosine is less or equal than 1, and cosine of an x is also less or equal than 1. So the expression that I see in front of me is going to be less or equal than absolute value of sine nx, because I dropped cosine, so I raised this expression. And I dropped the second cosine, so this should be plus absolute value of sine x. Well, but now I know that at the end statement, at the level n, the statement is true. So sine of nx, absolute value, is less than n times sine x. So this would be less than, so absolute value of sine of nx is less than n times absolute value of sine x, and still I have my plus absolute value of sine x left, and I can combine the two to get n plus 1 times absolute value of sine x. And that's exactly what I had to show, so that means that the induction step is okay. And so then the final conclusion is that absolute value of sine nx must be less than n times absolute value of sine x for all n in n by mathematical induction. And if I want to, again, I can put the shaded square here to indicate that I'm done. All right, so then in the next lecture, we're going to talk about rational numbers.